An LED flashlight, and I have to say I'm a bit suspicious about this light because it seemed too good to be true. It seemed too cheap. The listing says, LED torch flashlight, 2 light modes, rechargeable flashlight, tactical hiking torch. It says now £3.99. It was £3.29, and if you consider that typically it costs something like £3 to ship an object of this size by Royal Mail, that doesn't leave much for eBay fees and the raw materials. But this is rechargeable. It comes with a charger and an adapter, and the seller was UK Best Deals 592, but at this point in time, let's wait to the end of the video before we decide if it's a good idea to buy one of these. 8 available, 83 sold, and the feedback was all positive, which is good. The package it comes in is very fetching, mainly because it holds, it shows that sort of American style worker with the fist clenched, holding it like that. I think they've mistaken it for flashlight as opposed to flashlight. WH-008, 500 lumens. I have nothing really to indicate whether it is that intensity. It says 100 to 300 meter range. And the lamp life is up to 100,000 hours. And I have to say, up to starts at 0, so that's probably true. Interestingly, it says it uses 3 built-in 18650 lithium batteries, and I have a lithium battery here, and it would hold 1, it wouldn't actually hold any more than 1, because that would encroach into the sort of lens area, so I don't know what that's about. And the range it says here is 100 to 300 centimetres, which is considerably shorter than 100 to 300 metres. Now, I went out and tried it, and I tried it in the garden, and at a distance, this thing is useless for anything close range, because if I turn it on, it's got 2 intensity settings, low and high. And if I put this up against the ceiling now, you get this tiny little dot of light. And if I shine it across the room, you also get a tiny dot of light. And I took it outside, and over a distance of 10 metres, that's roughly 32 feet, the diameter of the beam was about this. It was approximately 400 millimetres or 16 inches. So it's good for spotlighting things. It's very impressive optics. But anyway, the first thing I tested when I got this was the electrical safety of this, because it just seemed so cheap. It came with this little adapter. The adapter is interesting. Hold on, let's bring the meter in. It's set to continuity. Beep, beep. Okay. Beep, beep, that's good. Let's check neutral. Neutral is continuity. Or should I say live is continuity? Neutral is continuity. Earth does not have continuity. That's odd, especially they've gone for the metal pin. Okay, it won't be brass, it will be brassy coloured metal stuff. Next thing to check is I'll plug this power supply in, and it's notable it's the type that when you plug it into the thing, the output seems to be going straight to the battery because you can see the green LED lighting, but I'm hoping there's charging circuitry in here for the following reason. Let me plug this in and unplug that from the light at the moment. So it lights up green to show it's charged, and I bring this in and I turn it to 20 volts, and this is supposed to be a 4.2 volt charger, and the output is approximately 6.5 volts, which would be quite high if it's going straight to the battery, so hopefully there is charging circuitry in there. But let us check that out. Let us open it and see what it's like. The end on the screws, and it's quite nice. It's a aluminium cover with glass, which is nice. That reveals a reflector, but nothing else, so I'm going to have to get into this in some other way. I don't see any screws. There may be screws under here, or maybe it just pulls apart. I can see a seam. Let's try brute force. Oh, here we go, here we go. I can see an 18650. Oh, that slides off, that's quite nice. One 18650. Let's get all the circuitry out of this. So the LED, it's quite neat. It's one of those fairly standard little things. It's got, it's got that little round plastic housing with an LED in the middle. And the circuit board in the back, which does have resistors. Let's take a look at those resistors. I'll just shove that battery back out the way. One of the resistors is 2.4 ohm and one is 12 ohm. Okay. This has no obvious charging circuitry on it. That's not good. That means that this lithium cell, it doesn't have any protection on it. It's potentially going to be charged up well above 4.2 volts, but we'll test that afterwards. We'll test the little power supply and see what we can find afterwards. But at the moment, this has a 10 ohm resistor on it and a 0 ohm link going out. So it's regulating the intensity to 2 levels down here. Then it's going up onto the circuit board. It's one of those white circuit boards that's quite hard to trace out. Right, tell you what, I'm going to pause momentarily. I'm going to reverse engineer this bit of it and then we'll take a look at the circuit. The circuitry is pretty much what you'd expect. It has the charger, which should be 4.2 volts. Now that I know there's no charging circuitry, I'm very suspicious about this charger, but we shall explore that afterwards. The charger goes straight to the lithium cell, which has no protection, and that then goes to switch as the off position, the low and high. The low puts it via a 10 ohm resistor, and for some odd reason, they've colour-coded positive red and negative blue, but that's okay. That's fairly typical. But then, because the LED is apparently the wrong polarity, they then switch to blue for the LED and red with the opposite polarity. But the LED, although it has a couple of resistors in the back, it seems to have a few different options for different applications. It has a 2.4 ohm resistor in line. So in the low setting, it's 12.4 ohm total resistance, and in the high setting, it's 2.4 ohms. And that equates at the mid-battery voltage of 3.7 volts, which it's at the moment, to a low level of 65 milliamps and a high of 250 milliamps, which is quite respectable, actually. That's okay. It's pretty much effectively sort of approaching a 1 watt LED torch once that's fully charged. So now I want to see what this charger's like. Let's brighten this image up. I want to put this under load because sometimes you get a rogue reading off this if it's not got a full load. But having said that, it will sort of terminate at 4.2 volts, but at that level the current will still trickle at a very low level, and if you leave the batteries on for a long time, it will potentially overcharge them, but we shall see. So at the moment I'm reading, not sure what the separation is in this unit, 6.6, wavering up and down, say 6.7 volts. Let's load that down. Let's bring in a variable resistor. Let's give it some, so that was about, well, we'll work it out afterwards. Let's put it down to 330 ohms and give that a decent load, and we'll see if it pulls it down. So I'll put that on there, that on that probe, and if this doesn't pull it down, if it's still above 4.2 volts, that's bad news. And we'll open the charger and take a look inside. It's still at the same voltage. If anything, it's slightly higher. That's ridiculous. That means that is absolutely... What was that? Was that 6.7 volts? 6.7. Let's work out what the current was there. That was a decent load. 6.7 I equals V over R divided by 3... What did I set it for? 330 ohm. That was about 20 milliamps I was loading it with. So I would have thought that would pull that down if it was just a floating voltage. Right, tell you what, let's open this up. Let's also open up this shonky little adapter that it came with. I mean, the torch itself at this point in time seems okay, but the charger and the adapter it came with are not okay. I'm guessing this will just pop apart. Let's pop it apart and see why the earth was not making a connection. Let's see if I can not stab myself in the process. I'm not really concerned about saving this thing. Is it glued together? Or... So I'm guessing that little stud there was supposed to make contact with the back of the earth connection, but didn't. It is a lot shorter than other studs. Okay. So that's just luck if any of these did make a connection. That's rubbish. I'll need a smaller screwdriver for this. Hopefully it's not a capacitive dropper inside. It's a little switch mode. Let's bridge out that capacitor because it is an unknown variable here. Actually, you know what? It's bridged. Rightio, what have we got? Not great isolation between the two sides. We do have an opto-isolator. We've got these little, let's zoom down on this so you can actually see it. We've got these little springy contacts that connect, bring power onto it. There's not great separation from the low voltage to high voltage side. They almost made an attempt in this area here, but they're not being too serious about it, and I'm not really surprised. It's just typical product of that type. Right, tell you what, I'm not necessarily going to reverse engineer this side of it, but I'm going to actually reverse engineer this side. I want to see what the circuitry is like and what their feedback's like. I can already see a little diode, possibly a Zener diode, in series with the opto-isolator probably here, and that will be the voltage reference. So they've obviously, I'm guessing, just used a completely wrong value. Right, tell you what, I shall be back in a moment. The reverse engineering is complete and it's kind of been fixed. Okay, if you want to try reverse engineering it yourself, here is the track layout flipped to match the component layout, but I've written the component values on if you want to take a snapshot. And if you want to see the other side of the circuit board, we have this notable things, this big output current limiting resistor, this Zener diode as a voltage reference, this opto-isolator feeding back to the control side, central resistor, single diode, big capacitor. Let's just look at the schematic. I'll zoom down for this. This is the primary side of that circuit. It's about the simplest you could make it. The incoming main supply comes in and it goes through a diode and charges this capacitor. It's 2.2 megafarad 400 volt death beam capacitor, and that provides a typical supply rail in the UK of about 350 volts. I don't know if this thing is rated for universal voltage. Hold on, I'm just going to check that. It is. It's rated for 100 to 250 volts, so that will cover quite a range. When the circuit is first powered up, current initially starts flowing through this very high value resistor and into the base of this transistor, and that causes this transistor to start turning on very, very slightly. When it does, current flows in the primary winding, and then that induces current magnetically in the feedback winding, and that couples back via this capacitor and resistor to the base of that original transistor and turns it on harder. When the magnetic field has reached the level, the desired level, which is set by this sense resistor, the current flowing through the primary winding, trying to induce the magnetic field through the transistor and then through that resistor, the voltage across this gradually rises until it reaches 0.6 volts. And that sets the maximum current through the primary. When it reaches 0.6 volts, it then turns this transistor on, which then shunts the base of that transistor and turns it off. The other thing that can turn that transistor off is the opto-isolator feedback, because all it does is it bridges the base to the emitter of that transistor to actually disable it. When the transistor turns off, the magnetic field collapses and the current flows effect from the opposite direction. It provides a nice, solid, sharp turn-off. It's a very neat and simple circuit. The other part of the circuit, when it does turn off, the magnetic field collapses and it actually induces current in this secondary winding, which then goes through this diode and charges this capacitor, which is not a death beam capacitor because it's only 10 volts, and that would be rubbish for death beams. The feedback, the voltage sensing circuit, consists of the optoisolator with a resistor across it to provide a continuous load for the Zener diode in series with it. I measured at 15 milliamps, 3.3 volts. It turned out the current was a lot higher, as I shall demonstrate shortly, because I did a little modification. But when the voltage exceeds the level of the combined forward voltage of this Zener diode, of this optoisolator, should I say, and the Zener diode, the Zener diode starts turning on, and the optoisolator then lights up. And when it lights up, it basically sends a signal to the other side saying the voltage is high enough to turn off. On the secondary side, this is just a bit of a show, this little bridge of resistors and LEDs. That's the charging and charged. We've got a 2.2 ohm high power resistor, that's a big resistor, which is just limiting the maximum current to the output. It's so that when you plug it into a flat battery, it's not going to try and shunt the output of the power supply. The green LED is pretty much lit all the time, and it doesn't light at very high intensity. The red LED is much more efficient. The red LED, through devious jiggling of component values to match, gives a very rough indication that when it's the voltage is being pulled down on this, it basically makes the red LED glow until it reaches vaguely above a certain threshold. It is extremely vague. It's not an accurate indication. If you've got these things, typically the red LED will go out and the green LED will come on way before things are fully charged. So the modification I made, let me show you it. I'm going to zoom out here. Well, I'll show you on here. I took the Zener diode out. Here's the Zener diode. I have taken this out. It is no longer in the circuit. And I replaced it initially with a forward biased LED with a voltage of about 1.8 volts. And the combined voltage, when I tried that, the feedback circuit appeared to be working because the voltage and the output dropped to approximately 3.3. Then, just out of interest, because I wanted to measure the current, because I thought that LED is glowing really brightly, I added another ordinary diode in series, just a 1N4148, to boost the voltage up a little bit to get it closer to the 4 volts. Not that I'm really going to use this power supply, but I thought it would be a good experiment to try. Let me bring that in. Let me try and not leave a huge sooty skid mark on my bench in the process here. So here is my fudge. Let's zoom down a bit again because that's better. Here is my fudged bit. Let's take the exposure, let's brighten that up. Here's the LED and the diode. In fact, I could do the current test again, but I shall show you this. I shall bring up a little thing that lets me plug this in at a funny angle. I shall plug this in here. It's not powered up at the moment. I shall attempt to, maybe I'll just plug it in about there. This is really not what you should do with high voltage power supplies on your bench, but this is what's happening with high voltage power supplies. So I'm going to plug that in. Look how bright that red LED has lit. It's pretty bright. The voltage in the output is now, and this is, I wouldn't even trust the separation, the electrical separation. It is now 4.2 volts. I think that would be acceptable for charging that lithium cell. But I want to show you the current that flows through that Zener diode type LED circuit and deduce what actually regulates that, what determines that current. So here is a little Unity UT10E, and keep in mind I do actually have this quite close to the transformer, which will be operated at fairly high frequency. I'm not really sure the best way to do this. Let's turn this on at the low current setting. Let's select DC amps and zero that out, and I shall plug this in and you'll see how much current is flowing through that LED. 28 milliamps. That's quite a lot. Well, that would have been flowing through that Zener diode. Maybe that's why the voltage on it was floating up, because it was effectively just passing quite a lot of current, and it was getting warm inside and it was affecting its forward voltage. Not really sure. But that is too much for a red LED, really. It's probably not okay for a red LED, but it's not something I'd actually really want to have running all the time. So, in summary, yes, what determines the current flowing through that? To be able to turn for the feedback from this little opto-isolator to be able to turn the other side off, it needs to have there's a certain, what they call a current transfer ratio, that the current in this will induce, say, an equal current in the transistor on the other side, but quite often they're not that efficient. So if the opto-isolators have to do a lot of work to actually shunt that transistor properly on the other side to turn it off, then the current through this LED will end up quite high. And basically the voltage will keep rising until it reaches the current at which that opto-isolator is turning on hard enough that it can actually pull down the base of the transistor on the other side. Things worthy of note. This transistor, let's write the values on. This is a 13001, and it carried an interesting surprise. This is an S8050. I initially, when I drew the schematic down here, I looked at the first 13001 transistor I came across, and it turned out the base collector and emitter were reversed, and I was thinking that's just not making sense in the schematic. I went online and I found a Russian website that basically said, be careful with the 13001, there's two pinouts that reverse base and emitter. Basically the transistor's turned round inside, and that seems to be a common thing, so that's something worth keeping in mind if you ever have problems with that. Oh, the opto-isolator is a DP817C. But there we go. The battery is on charge at the moment. Just hold on, I'm just going to go and check and see if it's charged yet. Yes, it's charged. Let's write the value on it if I can find a pen to do so. 500 milliamp hour. Or I could have just written pish on it, since that would really be pretty what it is. So there we go. This is all unplugged, just so you know. So I would say that if you've bought one of these flashlights, be very, very careful. Don't trust the charger. Check the voltage. If the voltage is more than 4.2 volts, then bin the charger. In fact, this charger will be going in the bin. It's not electrically safe. These horrible little chargers are just, they're not made with safety in mind. They're made down to a cost. The torch itself, the flashlight, it's nice enough. It's got a glass lens. It's got an amazingly accurate polished reflector. The LED's decent. Everything's good in it except the charger and the capacity of the battery, and the fact there's no protection. You could put a protected cell in, noting that they have just soldered onto the ends of the batteries. I just soldered onto their solder. So it's a shame, because the construction of the flashlight and the optics are good. It's just let down, notably, most utterly by the charger, and then the miserable capacity of the cell. If you have one of these, you may find you've already got a 4.2 volt charger for like remote control models and things like that with the same connector, and that could be used to charge it. But I would say measure the voltage across the output. If it's any more than 4.2 volt, then don't use it. With a protected cell, you could theoretically use higher voltage as long as they were current limited, and the cell would automatically shut off when it had reached its full charge. But there we go. It's a very odd little light. Very cheap, probably very cheap for a reason, but well worth taking apart anyway.